Okay, so a couple of questions. I'm not gonna answer anything about the true false questions because it would give them away. So so the true false, at least I don't think there's anything that's like confusing here. So true false is left up to you. Remember, when something is true, that means it is true as stated, right? For that situation as described, it is always true. When something is false, that means that there exists a counterexample, right? So something that satisfies everything that is stated in the statement in question, but contradicts the statement, right? Makes the statement uh, shows that the statement is false because it doesn't satisfy the conclusion. Okay, so anyway, the other question was I've gotten this question a lot, so actually I might send out an announcement. So Yekta asked the question of so it's for question 6. So for question 6, it's matrix multiple. That operation is not two operations, it's one. It's row replacement. So for question number 6 on exam 1, the first operation, I believe I wrote it as the first operation. Let me see here. The following sequence of 3 elementary row operations. That's swapping the first row and third column, multiplying second row by -2, and multiplying first row by 4 and adding it to this. Okay, all right. So I understand. Really, I should have put quotation marks around that. So the third row operation is a row replacement. Okay, and so that multiplying the first row by 4, adding it to the second row, replacing the second row with the result, that is all one thing. Okay, so the third row operation is row replacement, so it's all one thing. So multiplying by 4, and this is multiplying the first row by 4. So multiplying first row by 4, adding to second row, replacing second row. This is all one clause here. Okay, so this is all one step. Okay, this is row replacement. Yeah. So now you see the problem with explaining row replacement in words. Okay. Elements in a set means that a set has some objects in it, just like so. A vector space is a set. Remember that, and the objects in a vector space are vectors. Okay, so if something is in a vector space, it is an element of that vector space V as a set. So that's what's meant by that. Okay. Okay. Anyway, so yeah, first row is first row of A. I believe. I mean, what did I say? A is obtained from B, right? So this is being done. This is being done in the process. To you start at B, and you do those operations as written. And also, when you write, I want you to write A is equal to EFG times B. These EFGs should be matrices, right? So this should be some matrix, some matrix, some matrix. B, obviously, you don't know the matrix for. It's just totally general. But your answer to this, right, your final answer to this should be in this form. Should be matrices, matrix times matrix times matrix times B, right? That's how you'd write this. Okay. No, Yekta, it's a sequence of row operations. You're not starting over with B the whole time. You're doing these. You're applying them in a sequence. So you're applying it to the matrix before it, right? So you start with B and then you apply those operations in that order, right? Exactly in that order that I said. If you do it in a different order, you will get a different answer here. Okay. All right. So anyway, that's how it works. So this is how. No, you don't have to multiply these matrices. You can just leave them like that. Okay. Okay. So anyway, that's I figured number 6 would be an issue communicating it, because I've given similar problems like that in the past, and it's usually been an issue. But anyway, so I will. I know I've already gotten similar questions, so I'll refer people to this. If you have any other clarifying questions, you can email me. I will intentionally not be that helpful for other questions since it is an exam. So really, this only applies to like questions where you are confused about the problem statement itself. If your confusion is valid, that is so. So this number 6 is a good example of where it is definitely possible to be confused, and that's okay. So anyway, continuing on, the thing that I've been dancing around. In fact, there's a couple of questions on your exam that dance around this fact. It's the rank. Okay, the rank of a matrix. So before I can define the rank of a matrix, I need to define like one more thing just to kind of tidy up, and then I'll talk about the rank of a matrix. It turns out you're actually already familiar with the rank of a matrix. You just don't know it by this name. So, and yes, someone's asking, can you do the exam on tablet and turn it? I don't care how you did the exam. As long as you turn it in as PDF, that's fine. So I don't care in what format you actually did it. As long as it is a readable PDF submitted to ELMS by the deadline, then that's fine. Okay, so first definition is row space. So we already have the null space and the column space of a matrix. What's the row space? It's exactly what you think it is. Row A, the row space of some matrix. That's an n by n matrix. So this is the row space. Of some m by n matrix A. Is defined to be the set of all linear combinations of the rows of A, of the row vectors. Okay. Now, a couple of things here. You might have some complaints. I'm going to write the example, and then I'm going to alleviate your complaints. So here, let's do a quick example. So let's let A be the matrix. Let's see. Let's make it 4 by 5. So minus 2. I'm going to read row-wise. Minus 2, minus 5, 8, 0, 17. And the next one is, say, 1, 3, minus 5, 1, 5. And 3, 11, minus 19, 7, 1. And last row is, we'll say, 1, 7, minus 13, 5, minus 3. Okay. All right, so then we can write our row vectors as R1 through R4, and we write them in the way that you might have been accustomed to writing vectors in some other context. So maybe you've written vectors horizontally in, say, Calc 3, or maybe physics or something else. So you're going to immediately have a question here, which is, can I do this, right? Can I write vectors horizontally, right, like this, rather than vertically? And the answer is yeah, of course. of course you can write vectors like this. You would define all those vector operations in the exact same way. Right? So you define all those vector operations the same way, component-wise. It's just now your components are listed out horizontally instead of vertically, right? So it's purely an aesthetic difference here. And if you are concerned about this, well, there is a way that we can think about these being column vectors. How? All right. So first of all, what is the row space of A? Accordingly, well, it's the set of all linear combinations of row vectors of A, but that's really just the span of these row vectors. Okay, but I can hear it, I can feel it. You're having some reservations here. You're like, we've never dealt with row vectors like this before. Why can you just so seamlessly toss these in like that? And as someone said in the chat, yes, transpose, right? So the idea here is, well, the row space is not really a thing in the same sense that the column space and the null space are things. And the reason for that is the row space is actually just a column space. It's the column space of A transpose. Okay, so here's a big fact that's very important. So fact, the row space of A is really just the column space of A transpose. Right? So what this means is that you could have similarly started with the matrix A. If you wanted to find its row space and you didn't want to write horizontal vectors for whatever reason, you're allergic to horizontal vectors written out like this, you don't like these commas or something like that. So for whatever reason, you could look at A transpose first and then write out the column space of A transpose. But what are the columns of A transpose? So the first row of A goes to the first column of A transpose, so that vector is going to be -2, -5, 8, 0, 17. Hey, it's the same as R1, right? I've just written R1 horizontally here, but this vector would be written vertically instead. So that's it. Okay. All right. And so what if I just said that the row space is not really a thing in the same way that the column space and null space are things? Well, then what's the purpose of it? Okay, well, there is something nice about the row space that you can say that you couldn't say about, say, the column space. We saw that when you were dealing, for instance, with the column space of a matrix A, how did you find a basis for it, right? So how did you find a basis for the column space? Well, what you did is you looked at the entire span of all the columns, right? And then you basically saw which of those were redundant, right? You saw which of those were linear combinations of the others. You kept tossing those out until you ended up with a nice, convenient set. So, for instance, if you did a bunch of row operations, right, to identify the pivot columns, right, and then you identify those pivot columns with the columns in the original matrix, and then you said, my basis for the column space is those original columns, right? There was this issue. You couldn't list the vectors after you had done the row operations because those vectors might have, say, zeros. Say they all have zeros in the last slot, whereas a member of the column space might not, right? A member of the column space might have a 1 in its last slot. But if you were to try to use the pivot columns as they appear in the reduced row echelon form, those row operations have changed some of those entries in such a way that you can't recover everything just with linear combination. So the nice thing is the row space is something that's not affected in that way by row operations, okay, which you might expect in some ways if you like our good language that we've come up with to describe this, because we're calling it the row space, and I mean it's based on the rows, but okay. Anyway, so what's this theorem say? If two matrices A and B are row equivalent, So if two matrices are row equivalent, then their row spaces are the same. Okay. All right, the row spaces are the same. So if B is in row echelon form, so remember your textbook drops the row, it calls it just echelon form. So if B is in row echelon form, the non-zero rows of B form a basis of the row space. So the non-zero rows of B form a basis for the row space of A. As well as for that of B. Okay. Yeah. Right. So the thing is that note that this is not really quite true if you replace row space with column space here, right? If you have two matrices that are row equivalent, you can't really say that about their column spaces. Even though you're using row operations to find a basis for the column space, you can't say that the column space of the matrix you get in row echelon form is the same thing as the column space of the matrix you started with, right? That's the whole reason that we have to look back at the original matrix to find those basis vectors for the column space. You can't just use what you have here. So, for instance, we could go back to this example that we had used previously. So I'm going to call this A. So I'm going to call this matrix A. I'm not going to rewrite all of that. And it turns out that this A that we used before is row equivalent to B, which looks like this. So reading row-wise, again, this is 1, 3, minus 5, 1, 5. Second row is 0, 1, minus 2, 2, minus 7. Third row is 0, 0, 0, minus 4, 20. And last row is all zeros. Okay. So then what's a basis for the row space? So a basis for row A. So a basis for row A is, it's the non-zero rows. So it's the vector 1, 3, minus 5, 1, 5, 0, 1, minus 2, 2, minus 7. And one more, 0, 0, 0, minus 4, 20. Okay, so that's my basis for the row space of A. What's my basis for the column space? Okay, so what's my basis for the column space? Well, let's go back here. Here's my matrix A. Here's my reduced matrix put in row echelon form. Can you identify the pivot columns? Well, yeah, right. It's not too bad. In fact, I could continue reducing these if I wanted to. So here, I'll go ahead and reduce it further just because I want to do that for the next step anyway. But you don't need it for this step, but I'm just going to do it. So if I reduce this matrix further, the reduced row echelon form matrix reading row-wise is 1, 0, 1, 0, 1. And the first row next is 0, 1, minus 2, 0, 3. And third row is 0, 0, 0, 1, minus 5. And last row is still all zeros. Okay. Yeah, right. So exactly what chat is saying here, that I can identify the pivot rows or pivot columns very easily here, of course, but I could already see that it was 1, 2, and 4. And so I need to go back to my original matrix since I'm talking about the column space. I need to go back to my original matrix. 1, 2, and 4. Those are my vectors in the column space here, or those are my basis vectors for the column space. So that basis is first column, so -2, 1, 3, 1. Second column, so -5, 3, 11, 7. And last column, 0, 1, 7, 5. Hey, this is some additional practice for your exam, right? Because you're asked to do this on at least one problem on your exam. There's the basis for the column space of A. Now, let's do one more. Let's go ahead and do the null space of A, just because. So what's a basis for null A? How do I find it? Well, as we saw, I had already written this matrix in reduced row echelon form, which lets me look at the equation AX equals 0, right? So AX equals 0 is equivalent to, if I'm looking at this thing in reduced row echelon form, I can just write out the corresponding linear system. So this is x of 1 plus x of 3 plus x of 5 is equal to 0, and so on here. So I'm just going to write this out. So this is x of 1 plus x of 3 plus x of 5 is equal to 0. The next one was x of 2 minus 2x of 3 plus 3x of 5 is equal to 0. And then lastly, it was x of 4 minus 5x of 5 is equal to 0. Now, again, looking at this, how many free variables do I have? Well, I have 2, right? So x of 3 and x of 5 are going to be free. So then how many vectors in my basis for my null space am I going to get? 2, one for each free variable, right? One corresponding to x of 3, one corresponding to x of 5. So if I solve this, put this in parametric vector form quickly, so everything in terms of x of 3 and x of 5. So x of 1 is minus x of 3 minus x of 5. X of 2 is 2x of 3 minus 3x of 5. And x of 4 is 5x of 5. So putting this in parametric vector form, this means my basis for null A, I can write. I'm just going to go ahead and write it out. I'm going to save myself some time here. I get 2 vectors. What vectors are they? So x of 1 is going to be minus 1 times x of 3. X of 2 is 2x of 3. X of 3 is equal to itself because it's free. And x of 4 is 0x of 3, so that's 0. And then in the second slot, I would get minus 1 times x of 5. In the next slot, I would get minus 3 times x of 5. X of 3 is 0 times x of 5. Oh, sorry, this is a... wait, what am I doing here? There's an extra entry here. Right, there's 2 zeros here. Okay, next I have x of 4 is 5x of 5. And x of 5 is equal to itself, so that's 1. This is what happens when you try to shortcut this. Of course, you know, how did I get these numbers, right? I just rewrote this general solution. So here I ended up doing it anyway. So my general solution, which is x of 1, x of 2, x of 3, x of 4, x of 5, can be written as, I'm going to go ahead and write the linear combination. So this is x of 3 times minus 1, 2, 1, 0, 0, plus x of 5 times minus 1, minus 3, 0, 5, 1. All right, that's where I got this. Okay. All right. And so, looking at this, you know, there's something to be said here. Here's one final warning before I move on. So in this example, I reduced B to row echelon form. Once I had reduced B to row echelon form, the non-zero rows form a basis for the row space of A. Rows 1, 2, and 3 were non-zero. They are a basis. Now, because they're a basis, what does that mean? That means they're linearly independent. Okay? So they are. You could check. These first 3 rows are linearly independent. Does that mean that the first three rows of A are linearly independent? No. No. In fact, this third row is a linear combination of these two. Okay. So it doesn't mean that the it doesn't mean that the rows of A are linearly independent just because the rows of B are. Okay, that's a little tricky. So unlike for the column space where we do row operations and then we look back to the original matrix A, for the row space we do the row operations and then pick the rows that we have. We don't go back to the original matrix. In fact, if you go back to the original matrix, you're likely to get something that's wrong. Okay, for your basis, because you're going to get vectors that aren't linearly independent. Okay, now why did I go through all of that? We have been dancing around a quantity that makes describing a lot of this much, much easier. Okay, and so what is that quantity? I wrote it at the beginning of the lecture. That quantity is called the rank. Okay, so as I said, you have already seen this. So the rank, okay, of A is the dimension of the column space of A. Okay. Okay, so the question is, could a basis for row space A also be considered the non-zero rows of B in reduced row echelon form? Yes, that's fine. So reduced row echelon form is still it's a row echelon form still. Okay, it's just an even nicer one. So that previous theorem applies just as well. So yes, that's true. So once you have it in row echelon form, if you continue on, then everything you get, as long as it's in row echelon form, even if it's reduced row echelon form, will work as a basis for the row space. So you can continue doing any operations you want to do as long as it doesn't take it out of being a row echelon matrix. Okay. So the rank is the dimension of the column space. You're asked to find the dimension of the column space, on your exam, for instance, and we've done this several times now. So for instance, let's quickly, go back. What's the dimension of the row space in this example? Well, 1, 2, 3, right? 3 basis vectors. So dimension of row space is 3. What's the dimension of column space? 1, 2, 3. It's dimension 3. What is the dimension of the null space? 1, 2, dimension 2, right? Now, I mentioned to you before that you might notice a pattern. When you do a few of these examples, you might notice a pattern between the dimension of the column space and the dimension of the null space. Right? In fact, you might notice that the dimension of the null space fills out what is, we'll call it the gap or the hole left by, if there's anything left at all, fills out the gap left by the dimension of the column space. And so it's so important that it also has a name. The nullity, this is something that's not used that much. It's more an older name. So the nullity of A is the dimension of the null space of A. Okay, and so, like I said, I had asked you whether or not you noticed that there was a pattern. The next theorem I state is going to tell you exactly what that pattern is. Okay, when writing the basis for row A, is it necessary to write horizontally to be technically correct? No. You don't have to do that. You don't have to write them horizontally. If you write them vertically, that's perfectly fine. Just understand that what you're using there is the fact that the row space of A is the column space of A transpose. So if you're if you're very nervous about that, you can just state that fact and then write it using that identification. Okay, there's more flowery language that is better fit to describe exactly what's going on there, but we're not going to get to it in this course, unfortunately. So if you want to get to language that allows you to really, really make 100% sense of what's going on there, you have to take a more advanced linear algebra class. But yes, it's perfectly fine. Well, I can tell you on one thing. There's an easy way to identify a vector space with some other space that is like that's very similar to it. We'll call it its dual, and it turns out they're isomorphic. And so this changing between rows and columns is an isomorphism, which is why, so you understand isomorphism now, so that's why any computation we wanted to do in the rows, we could do in the columns just as well, right? As vectors, right? As vectors. So as vector spaces, those are the same thing. Okay. And yes, so as someone else pointed out, you could even use transpose of the vectors if you didn't really like it. So you could write them as columns and then put the little transpose thing there to say, well, they're rows, but I'm writing them as columns. So don't worry too much about that. You're not going to get points taken off for that. So anyway, this pattern that I asked you all to consider is called the rank nullity theorem. So the textbook just calls it the rank theorem. That's perfectly fine, but I'm used to it by the old name. And also it tells you exactly what it involves. It involves rank and nullity. Okay, so what the rank nullity theorem says is the dimension, or I should say the dimensions of the column space and the row space of a matrix A that's an m by n matrix are equal. All right, so that pattern that you saw in the first example, well, that was just a single example. You can't really call that a pattern. But it turns out that that's always the case. It's not an accident that the row space and the column space have the same dimension. This common dimension, i.e. the rank of A, all right, so rank A is also equal to the number of pivot positions in A. Right. And satisfies the equation that is not mysterious at all, because actually we've reasoned through it before, even though I didn't explicitly say it. So it satisfies the equation rank A plus the dimension of the null space of A is equal to what? Okay, let's just look at our example before I even write this. So going back to look at our example, we had our matrix A. We took our matrix A, we row reduced it. Here it is in row echelon form, or reduced row echelon form. Once we had it there, we could see that the first, second, and fourth columns of A had pivots in them. So the dimension of the column space is 3, right? There's the 3 column vectors of A that form the basis for the column space. All right. Well, what's the dimension of the null space? By definition, it is the number of non-pivot columns, right? So when you look at this, you have rank of A, which is the dimension of the column space of A. So in this case, that's 3, the number of pivot columns, plus the dimension of the null space, but the null space has a basis vector for every non-pivot column. That's every free variable, right? So every non-pivot column. So the question is, what is the number of pivot columns plus the number of non-pivot columns? Well, it's just the total number of columns, right? It's just n, the total number of columns. All right. And I mean, that's the proof, right? This has an important name and is actually very important, but once you set up this terminology, the proof is literally one line, right? Proof. Well, number of pivot columns plus number of non-pivot columns equals number of columns. Right? That's the proof. Okay, why is that the proof? Because the number of pivot columns is the rank of A. The number of non-pivot columns is the dimension of the null space of A. And the number of columns for an m by n matrix is n. QED, right? That's it. That's the proof. Okay. Yes, so that's right. That's another way of thinking about it, Gustavo. So n minus the rank of A is the dimension of the null space. That's right. Okay. And so this allows you to answer all kinds of questions conceptually. So there's all kinds of things that I could ask you based on this. I didn't include them on this exam. They will be included on your next exam. There will be a ton of questions I ask you about this because it really gives, there's really like infinite amount of conceptual questions I could ask you based on this. Okay. And so that's the that is the rank, or that's the rank nullity theorem, which ties in all this stuff together. So let's do a couple of conceptual type questions. Like I said, there's infinitely many of these that I could ask. So here's an example. So one. If A is a 7 by 9 matrix, okay, and the dimension of the null space of A is equal to 2, what is the rank of A? And second question, could a 6 by 9 matrix have a two-dimensional null space? So here's two types of questions that I could ask. Yeah, so first example, the answer is the rank of A is 7, right? So for number 1, rank of A plus dim null A is equal to the number of columns. It's 9. But if dim null A is 2, then the rank of A has to be 7. And so knowing something about the dimension of the null space immediately tells you something about the dimension of the column space, as long as you know how many columns you have, right? So if I give you a matrix and I say, oh, consider a matrix A that has, 5-dimensional null space, right? What's the rank of A? Well, if I don't tell you the size of A, you're going to have problems there. Okay. So you need to know the size. You need to know the columns. The number of columns here. Okay, so that's clear. How about the number 2? Could a 6 by 9 matrix have a two-dimensional null space? No, because by the rank nullity theorem, having a two-dimensional null space means the rank has to be 7. All right, so by number 1, no. All right, such a matrix, say B, would have to have rank 7. Okay, that's by 1. Okay, but the columns of B are in what space? If B is a 6 by 9 matrix, what space are the columns of B in? How many entries are in the columns of B? There's 9 of them, and they have 6 entries, right? So those are in R6, right? i.e., the dimension of the column space of B cannot be more than 6. All right, so rank B cannot exceed 6, but that's a problem, right? So that can't happen. Okay, so the answer to that is no. Right. Right. Yeah, so it's that. So the thing is that it's not just a property of 6 and 9 here, right? Like, could a 6 by 9 matrix have a blank dimensional null space? Well, that really depends on the dimension of the null space. So could a 6 by 9 matrix have a 3-dimensional null space? Then yes, right? Could a 6 by 9 matrix have a 3-dimensional null space? In fact, it could, right? Another question, slightly more general, is what dimensional null spaces are you allowed, right? Like if I give you the size of a matrix, what sorts of, how many dimensions of the null space are you allowed? Conversely, right, asking like what dimensions or what ranks you're allowed for a matrix to have, depending on knowing other info. This rank nullity theorem nails down what can happen. Okay. All right, and so as I said, there's going to be a ton of these examples you go over. So in discussion tomorrow, you're going to go over a lot of those, in fact. So now the thing that I wanted to do is now we've spent all this time coming up with all these notions, right? We talked about abstract vector spaces. That led us to finally talking about a basis for a vector space. That allowed us to define what it meant to have, say a basis for some subspace, and then talk about dimension. Right? We could talk about dimension of these things. Okay, and so this really shows why that abstract vector space approach is the right way, because it allows us to talk about, the subspaces of vector spaces, both, copies of Rn, or things that maybe don't immediately look like Rn to you. It allows us to talk about them all the same. We used the notion of a basis to define dimension, right? And now we've used dimension to define this rank thing. We have the rank nullity theorem that tells us a lot of conceptual info about the matrix, because we already know the things that are tied in with the column space and the null space of a matrix. And so this nice language allows us to conveniently add to the invertible matrix theorem. Okay. So this allows us to conveniently add to that list, that really, really long list that I showed you in the book. I didn't even write it down. So what I'm going to do is later, sometime before Wednesday, I will take pictures and upload, and the file will be called the invertible matrix theorem, that includes both the original invertible matrix theorem and this addendum. Okay, so invertible matrix theorem addendum. Okay, so the invertible matrix theorem went all the way up to L, I think. So we're going to start at M here. Okay, so what this is let A be an n by n matrix. Then the following are equivalent. Okay, so part M is the columns of A form a basis of Rn. That is equivalent to the statement that the column space of A is all of Rn. Okay. The O part is that the dimension of the column space of A is equal to n. That is also equivalent. The P part says that the rank of A is equal to n. The Q part says that the null space of A is the 0 subspace. And the R part says that the dimension of the null space of A is 0. Okay. All right. Okay. And yes, but I think this is the last addendum that we have here. So the first one goes through L. This second bit goes M to R, right? And so all of these things are equivalent to all the things in that previous list. Maybe I can find them real quick. And of course, some of these implications in both directions are actually really, really easy to see. Because ultimately, some of these implications, like the dimension of null space being 0, well, we've defined that to mean, right, the only time that dimension is ever equal to 0 is if the thing in question is the 0 subspace. That's by definition. And so R and Q being equivalent is trivial. That's actually just by definition. O and P being equivalent is also by definition. So let me, I think I can find this quickly enough. Here we go. Yeah, here's the first part. So invertible matrix theorem. So it goes A through L. So just quickly rattling off. All these are equivalent to that list I just wrote. So A is an invertible matrix. A is row equivalent to the n by n identity matrix. A has n pivot positions. The equation AX equals 0 has only the trivial solution. The columns of A form a linearly independent set. The linear transformation that sends x to A times x is 1 to 1. The equation AX equals B has at least one solution for each B in Rn. The columns of A span Rn. The linear transformation that sends x to AX maps Rn onto Rn, so it's an onto transformation. J and K says that there's one-sided inverse matrices. And so L says that A transpose is also an invertible matrix. So tack these on to those, and you get this huge invertible matrix theorem that says the second that you know one of this long list, you know all of them, right? And so what that says is that if you have a matrix that has rank n, right? So sometimes this will be called, in various contexts, especially even if A is rectangular, it's full rank. Full rank meaning it has the maximum possible rank. So you'll be asked several questions about that. Okay, so I'm more or less done with chapter 4. There's only one more thing now. So all of that build-up just gave us yet more ways to recast all of these questions about matrices in just one more light. Right, so one more thing in chapter 4. And after this, we will do the only thing that we're going to come across, or the first thing that we've come across since basically chapter 1 stuff that is like fundamentally different in some way. Okay, so one more thing in chapter 4, which is change of basis. So we have already seen this for the easy example. So we've already seen this. We've already seen a special case of this. And in past semesters, sometimes I would actually save the change of coordinates stuff until now and do it all at once. Because this is actually similar to the change of coordinates stuff that we did earlier. But the idea here is to be able to change bases, right? So instead of changing from basis to standard basis, I'm going to change between two bases. So, but instead of changing from some basis B, right, consisting of some basis vectors, B1 to Bn, to the standard basis, or in the other direction. Of Rn, we change from B to some other generic basis C. Okay. So this is the idea. All right. Okay, so I think that's all I'll say for today. So I'll finish chapter 4 up next time and might get to start a little bit on chapter 5 on Wednesday. But yeah, we will begin chapter 5 very soon, which is eigenvalues. Okay, which you may have encountered in some context before, but this is going to be the first thing that is like fundamentally different in terms of what you do, right? Everything from chapter 1 to 4, other than the determinant, which you still use some of the things that I'm about to say, but basically every question you could be asked is solvable by doing row operations on a matrix, right? So pretty much anything that you want to be asked from chapters 1 through 4 is solvable via row operations, right? Once you understand the language, that's basically what you're doing in every single question. You're doing row operations. So this, eigenvalues, eigenvector stuff is the first time in the course where you're going to do something that is not that. It's going to be different. Anyway, so I will see you all Wednesday. Remember, your exam is due tonight at midnight, so turn it in. Like I said, if you have any lingering questions that you're confused about the statement of some problem, you can ask me. If you send me questions asking, more about the substance of the problem itself, I'll intentionally be a little unhelpful. But anyway, that's how it goes. So so discussion tomorrow. You'll be going over rank nullity theorem, and on Wednesday we'll do change of basis, finish chapter 4. So I will see you all on Wednesday.